Okay, so this is a second mini lecture about the governing equations for transonic aerodynamics. And in the previous lecture, we've seen the full velocity potential equation for compressible flow. And we didn't do the derivation, we actually skipped the derivation. So in this mini lecture, we will derive the compressible velocity potential equation. So we'll see the procedure in here. And about 2D compressible inviscid flow, we have the governing equation, which start with continuity equation and the momentum equation. If we look at the continuity equation, rho is within the partial difference, which is different from the incompressible flow, because if it's incompressible, rho is a constant. It can be taken out. For example, water flow is incompressible, so rho should be taken out. And then eventually this rho can be cancelled because the right hand side is 0. And now we have the momentum equation. The momentum equation is also called the Euler's equation. If we consider the viscosity of the flow, we will have a bigger term about the viscosity. Then that's called Navier-Stokes equation. Okay. So for the inviscid flow, we have the Euler's equation. And now let's introduce the conditions about these three governing equations. First of all, the flow is compressible, and second, the flow is inviscid. What does inviscid mean? We're neglecting the viscosity, which means there's no boundary layer. We're just no boundary layer flow. Okay, and the three is irrotational. What does irrotational suggest? And I think I described it. It's physical suggestion in the previous lecture. Irrotational means there is no flow separation, and also there is no boundary layer, because if you have a boundary layer, there is a velocity shear, and then you have rotation through the mathematical definition. Okay, and similarly, since we are deriving the full velocity potential equation, we need to introduce the velocity potential. And the velocity potential is a similar definition as in the incompressible flow. So we have u equals partial phi partial x, v equals partial phi partial y. So let's start with the continuity equation. It is showing here. And now what we do is to expand the continuity equation. So we use the chain rule, it becomes 4 turns. And then we know there's a velocity potential, and it's defined this way: u equals partial phi partial x, v equals partial phi partial y. And then we just plug u and v into the expanded continuity equation. Okay, so then we have the continuity equation in the velocity potential form as second derivative of the velocity potential, right? Okay, so then what we do is do the reorganization. So we can see rho, which are not known because it's compressible flow, the density changes everywhere. So the target now is to eliminate this rho density. Okay, how can we do this? And what we do is, considering its compressible flow, one important feature is the Mach number, and Mach number, the denominator is speed of sound. So in a high-speed flow or in the compressible flow, if the flow is isentropic, then the speed of sound, it can be calculated this way: partial p partial rho equals a squared. A is the speed of sound, and then we can find partial rho partial x partial rho partial y for the above equation. Okay, so by plugging partial rho partial x partial rho partial y, and then we can get this equation. So the original continuity equation can be expressed by the velocity potential, but still we can see there is 1 over rho times partial p partial x and 1 over rho partial p partial y, which are in question. We don't know what are they. So let's see. We haven't used the Euler's equation, and perhaps that can be contributed to here. Okay. So now we have the momentum equation, And luckily on the right hand side, we have exactly same thing as what we got in the continuity velocity potential equation. Right, so now we just plug in the momentum equation into the continuity equation. So we can have this form of very long equation in velocity potential. Okay, so it's quite neat, I would say, if we do the reorganize everything, and then it becomes this very neat 2D full velocity potential equation. So now you see how it's derived. So the additional thing we used is the velocity potential and the speed of sound. And so since this is 2D, and do remember the conditions we apply to this at the beginning to this derivation. So we have compressible flow, inviscid flow, and the flow is irrotational flow, and the flow is isentropic. Okay. And then we also have the 3D form. I didn't do the derivation, but it's also very neat, and you can see the formatting here. So this is a derivation of 2D velocity potential equation.